January 17, 1940, Camden, New Jersey. An American engineer opens a wooden crate marked Urgent, War Department. Inside, a German radio pulled from a U-boat wreck off Iceland. He unscrews the chassis with trembling hands. What he finds makes his blood run cold. The vacuum tubes inside are half the size of anything America can produce. More efficient. More powerful. A year ahead. Maybe two. In that frozen moment, Harold Wheeler realizes a terrifying truth. America is about to enter the greatest war in human history, and we have no radio tubes worth a damn. No radar that can see far enough. No communications that can reach across oceans. No technology to coordinate the fleets and armies we'll need to survive. But this engineer doesn't know something yet. He doesn't know that in 18 months, American factories will invent a technology that doesn't exist and produce it by the millions. He doesn't know that this glass cylinder, no bigger than your thumb, will become the invisible weapon that defeats the Axis powers. He doesn't know that the Germans and Japanese are about to learn the hard way what American industry can do when it wakes up. This is the story of how America had no radio tubes in 1940. So RCA invented vacuum glass that amplified enemy transmissions, and won the war before the enemy even knew they were losing. January 17, 1940, Camden, New Jersey. The Hudson River lay frozen under a pale winter sun, and inside the brick fortress of the RCA Victor plant, the air tasted of solder smoke and machine oil. Engineers in gray coats moved between assembly lines like monks in a cathedral of industry, their breath visible in the unheated wings of the factory. The hum of lathes and stamping presses formed a mechanical choir, punctuated by the sharp crack of glass being sealed into metal bases. In a corner laboratory, a young engineer named Harold Wheeler stared at a wooden crate marked, Urgent, War Department, his hands trembling not from cold but from the weight of what lay inside, a German radio intercepted 3 weeks earlier from a U-boat wreck off the coast of Iceland. The device was a masterpiece. Compact. Efficient. Powered by tubes half the size of anything America could produce. Wheeler unscrewed the chassis with a jeweler's precision, and what he found made his stomach tighten. The enemy was a year ahead. Maybe two. The vacuum tubes inside, delicate glass cylinders no thicker than a cigarette, amplified signals with a clarity that American radios could only dream of. In that moment, surrounded by the antiquated bulk of RCA's peacetime inventory, Wheeler understood a truth that would ripple through the war effort like a stone through still water. America had no radio tubes worth a damn. Not for war. Not for the kind of war that was coming. This was not a story anyone wanted to tell. Not to Congress. Not to the public. Not to the generals who were already sketching plans for fleets and armies that would require millions of radios, thousands of radar sets, entire networks of communication that depended on a technology America had failed to perfect. The United States, land of Edison and Bell, of Marconi's wireless and Fessenden's broadcast, had sleepwalked into obsolescence. While Europe burned, American engineers had been building radios for living rooms and dance halls. For soap operas and swing music, for a peacetime that no longer existed. The tubes they produced were heavy, fragile, power-hungry relics designed for a world that had vanished the moment Hitler crossed the Polish border. But this was also a story about what happens when a nation wakes up. When necessity becomes the mother not just of invention, but of transformation. When engineers stop asking, can we, and start asking, how fast? In the 18 months between that frozen morning in Camden and the fall of 1941, American industry would accomplish what seemed impossible. It would invent a technology that didn't exist, scale it to mass production, and deploy it across 2 oceans. It would turn radio tubes into weapons. It would make glass and metal amplify not just signals, but survival itself. And in doing so, it would hand the Axis powers a defeat they never saw coming, not on a battlefield, but in the invisible war of wavelengths and frequencies, in the silent struggle for electromagnetic dominance that would determine who could coordinate fleets, who could detect bombers, who could whisper orders across thousands of miles of darkness. The Germans and Japanese expected to face American muscle. They found American ingenuity instead. And the weapon that beat them wasn't forged in steel. It was blown from glass, evacuated to vacuum, and sealed with a prayer that physics would hold. The problem was older than the war. It was older than the Depression. It stretched back to the very birth of radio itself, to the early 1900s when inventors and tinkerers first learned to make electrons dance. A vacuum tube, called a valve in Britain, was a simple thing in theory. Take a glass bulb, pump out the air, seal in a filament and a plate, heat the filament until it boils off electrons. Apply voltage, and those electrons leap across the vacuum, creating a current you can control. amplify it, modulate it, turn whispers into shouts. But theory and practice were separated by an abyss of engineering nightmares. The glass had to be pure, free of impurities that would poison the vacuum. The seals had to be perfect, or air would leak in and the tube would die in days. The filament had to glow at exactly the right temperature, too hot and it burned out, too cool and it couldn't emit enough electrons. The metals had to be chosen with atomic precision, thoriated tungsten for the filament, nickel for the grid, copper for the plate. Every material had to survive repeated heating and cooling, thermal expansion and contraction, the brutal physics of a tiny sun burning inside a fragile glass envelope. By 1940, American manufacturers had mastered tubes for one purpose, entertainment. RCA, General Electric, Sylvania, and a dozen smaller firms churned out millions of tubes each year for home radios, for phonographs, for the new miracle called television. These tubes were large, as long as a man's thumb, as wide as a silver dollar. They consumed power like drunkards, heating up living rooms in summer and requiring massive batteries in portable sets. They were fragile, shattering if dropped, dimming with age, needing replacement every year or two. But they worked well enough for their purpose. You could listen to Roosevelt's fireside chats. You could tune in Glenn Miller from a ballroom in Manhattan. You could hear the war in Europe described in the clipped tones of Edward R. Murrow, and then turn the dial to something lighter. The military had radios, of course. The Army's SCR-194 backpack set weighed 35 pounds and had a range of 3 miles on a good day. The Navy's shipboard transmitters filled entire rooms, required dedicated generators, and still couldn't reliably reach across the Atlantic. These were radios designed for a pre-war world, for garrison duty and coastal patrols, for a military that moved slowly and fought predictably. They were not designed for blitzkrieg. They were not designed for carrier task forces scattered across the Pacific. They were not designed for the kind of war where coordination meant survival and silence meant death. Then came the German radio. The one Wheeler opened in his Camden laboratory. Its tubes were miracles of miniaturization. They used less power, produced more gain, operated at higher frequencies. The Germans had been forced to innovate by necessity. Their military needed portable equipment that could keep pace with fast-moving tank columns and paratrooper drops. They needed tubes that could survive being dropped from aircraft, dragged through mud, frozen in Russian winters. So German engineers at Telefunken and Siemens had compressed and refined, had learned to make glass thinner and seals tighter, had developed new cathode materials that required less heating current. American engineers studied these captured German tubes the way archaeologists study artifacts from a superior civilization. They X-rayed them. They tested them to destruction. They measured every dimension, analyzed every alloy. And slowly, reluctantly, they compiled a list of everything America couldn't do. Couldn't make glass that thin without it shattering. Couldn't seal metals to glass with that precision. Couldn't manufacture cathodes that efficient. Couldn't produce the required tolerances at any reasonable cost. The Army and Navy sent representatives. Polite men in uniforms who asked polite questions that weren't really questions at all. How long would it take to copy the German designs? Could existing factories be retooled? What about quality control, about training workers, about sourcing materials? The engineers gave polite answers that weren't really answers. Years, maybe, possibly never. The German tubes represented not just incremental improvements but fundamental rethinking. You couldn't copy them. You'd have to invent them all over again, and hope you got lucky. But luck, as it turned out, had a name. It had several names, actually, scattered across the industrial corridor between New York and Philadelphia. Men like Harold Wheeler, who had spent a decade designing radio circuits and knew vacuum tubes the way a pianist knows keys. Men like Benjamin Dudley at Western Electric, who understood glass chemistry at the molecular level. Men like Ernst Alexanderson at GE, the Swedish immigrant who had worked with Steinmetz and knew more about high-frequency alternating current than anyone alive. These were not the famous names of the war. Not the Pattons or Eisenhowers, not the Oppenheimers or Groves. These were engineers who would never appear in newsreels, whose work would be classified until the war ended and forgotten soon after. They met in conference rooms that smelled of coffee and cigarettes. They covered blackboards with equations and sketches. They argued about electron trajectories and thermal coefficients, about whether to use oxide cathodes or thoriated tungsten, about whether miniaturization was worth the loss of power handling capacity. And gradually, through the winter of 1940 and into the spring, a plan emerged. Not a plan to copy the Germans. A plan to leapfrog them. The breakthrough came from an unexpected direction. The Navy's desperation for radar. British scientists had shared the cavity magnetron, a revolutionary device that generated microwave frequencies powerful enough to detect aircraft at 40 miles. But the magnetron was useless without tubes that could amplify and process those microwaves, tubes that could operate at frequencies measured in hundreds of megahertz, far beyond anything commercial radio required. The Navy needed these tubes yesterday. It needed them in quantities that didn't exist. It needed the impossible. RCA accepted the contract in April 1940, and with it the burden of inventing an entire category of vacuum tube from scratch. They called it the 6AC7, and it would become the most manufactured tube of the war, 30 million units by 1945. But in April 1940, it was just a specification on paper. A fantasy. The requirements read like science fiction: operate reliably at 100 MHz. Gain of at least 200. Survive shock of 50 Gs. Function from -40 degrees Fahrenheit to +160 degrees Fahrenheit. Last for 500 hours minimum. Be manufacturable by unskilled labor in quantities of thousands per day. Wheeler assembled a team. Young engineers mostly, men too valuable to be drafted, though several volunteered and were rejected. They worked 16-hour days, 7 days a week. There was no separation between work and life, between the laboratory and the world. Their wives brought them dinner in brown paper bags. Their children learned to fall asleep to the sound of their fathers coming home past midnight, smelling of solder and exhaustion. The first problem was the envelope, the glass bottle that held everything. Commercial tubes used ordinary soda-lime glass, cheap and easy to work with, but it couldn't handle the thermal stresses of high-frequency operation. It contained impurities that poisoned the vacuum. Wheeler's team needed something better. They found it in borosilicate glass, Pyrex, developed by Corning for laboratory glassware. It could withstand sudden temperature changes. It was chemically inert. But it was also harder to work with, requiring higher temperatures to melt and seal. Corning's engineers said it couldn't be done. Not at scale. Not with unskilled workers. Borosilicate required precision flame work, the kind of skill glassblowers spent years learning. RCA's response was American in its audacity: automate it. Build machines that could do what craftsmen did, but faster, more consistently, 1,000 times a day. They designed carousel systems where glass tubes rotated through stations, each one performing a single operation: heating, shaping, sealing. They developed new torch designs that mixed oxygen and natural gas in exact ratios, creating flames of precise temperature. They invented sensors that could detect a bad seal by measuring the rate of vacuum loss, rejecting failures before they ever left the line. The filament was next. German tubes used oxide cathodes, barium and strontium oxides coated on nickel, that required minimal heating power. American manufacturers had never mastered the technique. The oxides were finicky, degrading if exposed to even trace amounts of oxygen, requiring precise activation temperatures. Wheeler's team spent months testing combinations, baking samples in ovens, measuring emission under microscopes. They consulted with materials scientists at MIT, with chemists at Bell Labs, with anyone who might know something about ceramic chemistry and electron physics. The breakthrough came from an unexpected source: a retired GE researcher named Irving Langmuir, who had won the Nobel Prize in 1932 for his work on surface chemistry. Langmuir had studied oxide cathodes in the 1920s and abandoned them as impractical. But war changes what's practical. He came out of retirement to consult, spending weeks in the RCA labs, his shock of white hair unmistakable among the younger engineers. He taught them the secret: thorough degassing. Bake the entire tube assembly at high temperature in vacuum before sealing, driving out every molecule of adsorbed gas. Then coat the cathode and activate it in a pure helium atmosphere before evacuating to final vacuum. The process added steps, added cost, but it worked. By summer, they had prototype tubes that met most of the specifications. Almost. The shock resistance was marginal. The lifespan was shorter than required. The gain varied too much from unit to unit. But they were close. Close enough that the Navy ordered production to begin immediately, using a manufacturing process that was still being invented. Close enough that other branches of the military started placing orders: the Army for radar operators, the Air Corps for navigation systems, the Signal Corps for portable field radios. RCA broke ground on a new factory in Harrison, New Jersey, in July 1940. It was complete by October, an industrial cathedral 3 stories tall, covering 8 acres, employing workers who 3 months earlier had been unemployed, who had been clerks and seamstresses and farm boys. The company recruited women especially, believing their smaller hands better suited to delicate assembly work. They built a training center where new hires spent 2 weeks learning to handle glass and wire, learning to spot defects, learning the rhythms of production lines that never stopped. The factory operated around the clock. 3 shifts, 8 hours each, with 15 minutes overlap for handoff. Workers clocked in to find their stations prepared by the previous shift, materials staged, machines warmed up, defect logs updated. They worked under bright lights, magnifying glasses clamped to their benches, assembling components so small they sometimes needed tweezers to handle them. A single tube required 27 separate operations, from stamping the base pins to evacuating the envelope to final testing. Each operation had to be perfect. A misaligned grid would cause oscillation. A contaminated cathode would fail within hours. A weak seal would let air leak in, destroying the vacuum. Quality control was obsessive. Every 100th tube was pulled for destructive testing, deliberately overheated, overvolted, shaken until it failed. Inspectors recorded the failure modes in thick ledgers, and engineers pored over the data each morning, looking for patterns. A batch with weak seals. Investigate the glass supplier. A run with low gain. Check the cathode coating thickness. The feedback loop was continuous, relentless, unforgiving. And slowly, through the fall of 1940 and into 1941, production scaled up. From 100 tubes a day to 1,000. From 1,000 to 10,000. By Pearl Harbor, RCA's Harrison plant was producing 50,000 tubes daily, and still it wasn't enough. The Navy alone needed 1 million tubes for the radar sets being installed on every warship. The Army needed millions more for field radios and fire control systems. The British were pleading for supplies, their own tube factories devastated by German bombing. Other manufacturers joined the effort. Sylvania, General Electric, Raytheon, Tungsol, companies that had been commercial rivals now shared blueprints and techniques, cross-licensed patents, sent engineers to help each other solve production bottlenecks. The government facilitated, sometimes forced, this cooperation. This was not a time for competitive advantage. This was a time for survival. German intelligence knew something was happening. They intercepted communications about tube production, about new radar installations. But they misunderstood the scale. They assumed American industry was simply copying German designs, trying to catch up. They couldn't imagine the reality, that American engineers had not copied but innovated, had created tubes that in some ways surpassed German equivalents. Tubes that were easier to manufacture, more reliable in field conditions, compatible with a vast network of equipment being produced simultaneously. Japanese intelligence was even further behind. They had their own vacuum tube industry, sophisticated by Asian standards but isolated from Western developments. Japanese tubes were adequate for short-range communications, for coastal defense radars. But they consumed too much power for shipboard use, failed too often in tropical humidity, couldn't handle the frequencies needed for airborne intercept radar. Japanese engineers knew they had a problem. They didn't know how big it was. In early 1942, after the initial Japanese victories in the Pacific, American submarines began recovering equipment from sunken ships. Radio sets, radar units, electronic gear of all kinds. Navy intelligence established a facility in Hawaii dedicated to analyzing captured Japanese electronics. What they found was simultaneously encouraging and terrifying. Encouraging because Japanese tubes were inferior, larger, less efficient, poorly sealed. Terrifying because Japanese forces had still managed to achieve stunning victories with inferior equipment, which raised uncomfortable questions about American tactics and readiness. But the tide was turning, invisibly, in the electromagnetic spectrum. By mid-1942, American warships carried radar sets that could detect aircraft at 70 miles, surface vessels at 20. Japanese ships, when they had radar at all, could barely manage half those ranges. American pilots had radio navigation systems that could guide them home through storms and darkness. Japanese pilots navigated by dead reckoning and hope. American ground forces had portable radios that worked across jungle and desert, that let companies coordinate with battalions, battalions with divisions. Japanese forces relied on runners and flags, on telephones that required laying wire under fire. The difference wasn't dramatic in any single engagement. It was cumulative, persistent, relentless. American forces could coordinate better, react faster, concentrate firepower more precisely. They could find the enemy before being found. They could call for air support from over the horizon, for artillery fire from positions the enemy didn't know existed. The radio tube, that unglamorous glass cylinder, that mass-produced miracle, had become a weapon as important as the rifle or the bomb. German soldiers began noticing too. On the Eastern Front, where Wehrmacht units had grown accustomed to electronic superiority, they started encountering Soviet equipment that seemed suspiciously advanced. Radios that worked too well. Radar that tracked too accurately. What they didn't know was that much of this equipment was American-made, shipped through Persia under Lend-Lease, carried across deserts and mountains to reach Soviet forces. The tubes inside bore Cyrillic markings, but they were born in Harrison, New Jersey, in Emporium, Pennsylvania, in the same factories that supplied the Pacific Fleet and the Army Air Forces. By 1943, American tube production exceeded 10 million units per month. The factories had evolved into precision ecosystems, with their own supply chains, their own culture, their own pride. Workers wore lapel pins indicating production milestones, 1 million tubes, 5 million, 10 million. They saw newsreels of battles where their work mattered, where radar had detected a Japanese attack in time to scramble fighters, where ship-to-ship radio had coordinated a destroyer screen that broke up a submarine wolf pack. Some of the workers were women whose husbands or sons were overseas. They knew, with an intimacy that transcended propaganda, that the tubes they assembled might save lives they loved. Quality control wasn't just a job requirement, it was a moral imperative. Inspectors rejected tubes with a fierceness that sometimes seemed excessive, but no one complained. Better to scrap a tube in Harrison than have it fail in the Coral Sea. The tubes themselves evolved rapidly. The 6AC-7 was followed by improved variants, the 6AC-7W for wideband applications, the 1852 for vibration resistance, the 6AK-5 for even higher frequencies. Each improvement was incremental, but together they represented a compounding advantage. By 1944, American radar could detect aircraft at 150 miles. By 1945, proximity fuses, tiny radio tubes packaged inside artillery shells, were destroying German V-1 buzz bombs in mid-flight, a feat that seemed impossible to the engineers who first heard the requirement. The Germans tried to respond. They designed new tubes, built new factories. But they were fighting a losing battle against American industrial capacity. Where RCA could iterate through a dozen design variants in a month, Telefunken required a quarter. Where American factories could absorb losses from bombing raids by shifting production to alternate sites, German factories had no backups. And most critically, Germany lacked the raw materials, the high-purity nickel, the special glasses, the thorium and barium compounds that modern tubes required. These materials came from mines in Africa, from refineries in South America, from chemical plants in locations the German military could no longer reach. Japan's position was even worse. By 1944, American submarines had severed most of Japan's trade routes. Raw materials for tube production, tungsten from China, nickel from the East Indies, even basic industrial chemicals, stopped arriving. Japanese factories struggled to maintain production of obsolete tube designs, let alone develop new ones. Japanese radar sets failed at increasing rates, their tubes dying from contamination, from poor seals, from cathodes that couldn't maintain emission. And American forces noticed. They noticed that Japanese radar warning was sporadic, unreliable. They noticed that Japanese aircraft had trouble finding targets at night. They noticed that Japanese naval formations blundered into ambushes that radar should have detected. The invisible advantage was becoming decisive. There was an irony that American engineers appreciated, though they rarely spoke of it. The vacuum tube was a borrowed technology. Lee de Forest had invented the Audion in 1906, but he'd built on Fleming's diode, which had built on Edison's observation of thermionic emission. The theoretical foundation came from J. Thomson's discovery of the electron, from Planck's work on blackbody radiation, from a web of international scientific exchange that spanned decades and borders. The Germans had contributed to this knowledge. So had the British, the French, the Russians. Science was supposed to be universal, a shared human endeavor transcending politics. But war had shattered that illusion. The same physics that powered radios also guided bombs. The same electrons that carried music also detected targets. Knowledge, it turned out, wasn't neutral. It was power, and power belonged to whoever could deploy it fastest and most effectively. American engineers struggled with this sometimes, late at night when the factories were quiet. They were building weapons, even if those weapons were made of glass and wire rather than steel and explosives. They were enabling death, even if indirectly, even if in service of a cause they believed just. Some found justification in the nature of the enemy, in the cruelties of Nazi ideology and Japanese militarism. Some simply didn't think about it, focused on technical problems that had clear solutions, on the satisfaction of making things work. But others recognized a deeper truth, that the war was being won not by individual genius but by collective capacity, by an industrial system that could absorb knowledge, scale production, iterate designs, and deploy solutions faster than any other nation on Earth. The vacuum tube was a perfect symbol of this. No single person had invented it. No single insight had made it possible. It was the product of decades of incremental progress, of scientists and engineers building on each other's work, of manufacturers learning to control processes at finer and finer tolerances. This was America's secret weapon, not any particular technology, but the ability to develop and deploy technology at scale. Germany had brilliant engineers, America had thousands of competent ones. Japan had sophisticated laboratories, America had an industrial base that dwarfed the rest of the world combined. The Soviet Union had raw courage and overwhelming manpower, America had logistics that could supply that manpower with the tools to win. The vacuum tube illustrated this perfectly. Between 1940 and 1945, American manufacturers produced over 2 billion vacuum tubes. 2 billion tiny miracles of glass and metal, each one representing hours of labor, grams of rare materials, kilowatts of electricity. They powered radios and radar sets, guided bombers and proximity fuses, enabled communications networks that spanned oceans. They failed constantly, the average tube lasted perhaps 1,000 hours, but the supply was inexhaustible. When one died, you pulled it out and plugged in another. The factories in Harrison and Emporium and a dozen other cities never stopped, 3 shifts a day, 7 days a week, for 5 years. German soldiers who were captured late in the war, who had fought on multiple fronts, sometimes spoke of their confusion. They had expected American forces to be soft, unprepared, reliant on material superiority but lacking the discipline and skill of professional soldiers. What they encountered instead was a military machine that combined material superiority with competent execution, that made fewer mistakes because its communications worked, its intelligence was better, its coordination was seamless. Japanese survivors of naval battles told similar stories. They had trained for night combat, for close-range torpedo attacks where their superior optical equipment and crew skill would prevail. But American ships detected them first, from ranges where optical equipment was useless. Radar gave Americans the gift of sight in darkness. The ability to know where the enemy was before the enemy knew they were detected. In the confused melees of the Solomon Islands campaign, this advantage was often measured in minutes, just enough warning to turn toward the threat, to ready weapons, to survive the initial contact and fight back. The radio tube didn't win these battles alone. Men still had to fight, to make decisions under fire, to endure fear and exhaustion and the random cruelty of high explosives. But the tube changed the odds, shifted the balance, made survival more likely and victory more achievable. It was an unfair advantage, and American forces used it without apology. After the war ended, after the factories fell silent and the engineers returned to peacetime pursuits, the full story began to emerge. Historians catalogued the innovations, the production statistics, the web of connections between laboratories and factories. They discovered that the vacuum tube program had touched nearly every aspect of the American war effort. It had enabled radar, which had enabled strategic bombing and naval supremacy. It had enabled secure communications, which had enabled the coordination of armies across continents. It had enabled electronic computing, which had broken codes and calculated bombing tables and managed the logistics of global war. But the vacuum tube story didn't end in 1945. The technology developed for war transformed peacetime. Television became practical, exploded into American living rooms, changed politics and culture. Radio evolved from a luxury to a ubiquity, becoming the soundtrack of the 1950s. Computers, built from thousands of vacuum tubes, began automating calculations and data processing, laying the groundwork for the information age. And quietly, in laboratories and universities, engineers were already working on the tube's successor. The transistor, invented at Bell Labs in 1947, would eventually make vacuum tubes obsolete. It was smaller, more reliable, consumed less power, generated less heat. By the 1960s, tubes were disappearing from consumer electronics. By the 1970s, they were rare even in industrial applications. But the lessons of the tube era persisted. The manufacturing techniques developed to produce billions of tubes, the precision assembly, the quality control, the supply chain management, carried over to transistor production and then to integrated circuits. The engineers who had learned to work with glass and metal adapted to work with silicon and doped semiconductors. The culture of rapid innovation, of scaling from prototype to mass production in months rather than years, became embedded in American industry. There's a memorial of sorts in Harrison, New Jersey, though few people know its significance. The RCA factory still stands, converted now to office space and light manufacturing. A plaque on the wall, installed by the local historical society, notes that the building produced vacuum tubes during World War II. It doesn't mention the quantity, 30 million 6AC7 tubes alone. It doesn't describe the 3-shift days, the women with magnifying glasses, the obsessive quality control. It doesn't explain that the glass cylinders made here helped win the war. But sometimes, in the evenings when the autumn light slants through the old factory windows, you can imagine it. The carousel machines rotating, the torches flaring, the steady rhythm of production that never stopped. You can imagine the workers, young and old, men and women, carrying their lunch pails, trading gossip and rumors, worrying about loved ones overseas. You can imagine the engineers in their laboratory, staying late again, chasing some improvement that might matter, that might save lives. And you can understand, if you look carefully at the history, that this building was a battlefield. Not in the conventional sense, not with weapons and uniforms and medals. But in the deeper sense, a place where the outcome of the war was determined, where American industrial capacity confronted Axis aggression and prevailed. The weapons forged here were made of glass, evacuated to vacuum, sealed with techniques that had been invented months earlier by people who weren't sure they would work. The Germans expected American factories to produce tanks and ships. They did. The Japanese expected American laboratories to focus on bombs and bullets. They did. But no one expected what actually happened, that American industry would take an obscure component of radio technology and turn it into a decisive weapon, that it would solve problems thought unsolvable, that it would scale production to levels that seemed impossible. This was the nature of American abundance. Not just having more, though quantity mattered, but having the flexibility to pivot, to innovate, to identify what was needed and build it faster than the enemy could respond. The radio tube of 1940 was inadequate. By 1942, it was superior. By 1944, it was enabling technologies, radar, proximity fuses, secure communications, that the Axis powers couldn't match. And in the end, that made all the difference. Not in a single decisive moment, not in one dramatic battle, but in the accumulation of small advantages that became overwhelming. Better coordination meant fewer losses. Better detection meant earlier warning. Better communication meant more effective use of forces. The radio tube didn't win the war, but it helped win it, in ways large and small, in the Atlantic and Pacific, in Europe and Asia. The engineers who made this possible rarely spoke of their work afterward. It had been classified during the war, and even after declassification, it seemed too technical, too mundane to be interesting. They had made glass tubes. They had assembled metal components. They had tested and measured and improved. It wasn't glamorous. It wasn't the stuff of movie heroics. But it was essential. And in its quiet, technical way, it was heroic. Because these engineers and workers had done something remarkable, they had taken a technology that didn't exist and made it real, had scaled it from laboratory prototypes to billions of units, had sustained production through shortages and setbacks and the grinding exhaustion of wartime shifts. They had, in their way, defeated an enemy that never saw them, that never fired a shot at their factories, that didn't understand it was being beaten until too late. This is the forgotten victory, won in factories rather than fields, with vacuum pumps rather than rifles, by civilians in work coats rather than soldiers in uniform. It's a victory worth remembering, not for its drama but for what it reveals about the nature of modern war, about how nations win conflicts in the industrial age. Superior strategy matters. Better tactics help. Brave soldiers are essential. But underneath it all, supporting everything else, is the unglamorous work of making things, making them well, making them in quantity, making them when they're needed most. The radio tube was just glass and wire and vacuum. But in the hands of American engineers and workers, it became something more, a symbol of what free people can accomplish when they're threatened, when they're united, when they turn their collective ingenuity toward a common purpose. The Germans and Japanese learned this lesson the hard way, one failed radio at a time, one radar contact they didn't detect, one intercepted communication that turned the tide of battle. And in the wreckage of their defeat, if they looked carefully enough, they might have found the evidence. Millions of small glass tubes, marked with American manufacturer codes, still functioning in the radios and radar sets that had helped destroy them. The tubes didn't boast or explain. They just worked, amplifying signals, enabling communication, doing the invisible labor that won the war. That's the final irony. The most decisive weapon was the one no one saw, the one that left no dramatic footage, the one that historians initially overlooked. But it was there, in every American ship and plane and forward command post, a tiny glass miracle doing its job, hour after hour, until the war was won and the lights came back on and the factories finally fell silent. And then it was forgotten, except by the engineers who made it, who sometimes held one in their hands years later, found in a drawer, salvaged from old equipment, and remembered what it meant, what it had cost, what it had accomplished. That small glass tube, no bigger than a thumb, lighter than a letter, as fragile as a promise. The weapon that America had to invent because it didn't exist. The weapon that, once invented, changed everything.